keep going, read through the important notes, but really you can summarize a lot of this graphically. So read through your notes, and then we come to this gorgeous thing called an equilibrium constant. Right, lock in key knowledge, KK, key knowledge. You will not go near an equilibrium SAC, you will not go near a VCAA exam without absolutely knowing that if you've got a general equation expressed as coefficients are little letters and the reactants and products are capital letters. So look at what that does. It's products concentrations over reactants. Don't get that wrong. About 10% of students get that the wrong way round because, of course, reactants in an equation are on the left, come first, products are on the right, come second, so they put reactants over the products. Easy mistake to make. About 10% of students have not done enough of these to drill that. So there's your mental picture when you're doing an equilibrium constant, K. So they've called it K equilibrium here. In other places in these notes, they'll call it KC. That just means an equilibrium constant using concentrations. That's what the little c is standing for. And that will cover all VCAA questions. There are other ways of doing an equilibrium constant. You do not have to know about them. So this probably should have been KC if you were going to have anything here. But the EQ is short for equilibrium. We'll use that from now on as an abbreviation, save us writing it out. So they must be concentration at equilibrium. Now you can tell from the above graphs, it might take a while to get to equilibrium. So it might be possible to measure the concentrations sometime before it reaches equilibrium. So you could still write the same expression, but it would be called a concentration fraction. It looks identical. I'm going to want a symbol for that. The next couple of pages will use the symbol Q. I find that really foolish. Q we're going to use, you've seen it used in the calculations for Coulomb, for current. Why would I suddenly use Q again and run the risk of you thinking it was something to do with electric current? I'm going to use C little f for concentration fraction. And for that reaction, it equals concentration of C raised to the power C. Concentration of D, write it out with me so you've got this practice. Products again on the top line, over the concentration of A raised to the power A times the concentration of B raised to the power B. You can work out the value of that quotient at any time you like. That's why they call it Q, because it's a quotient, but that's not really a familiar name in your vocabulary, and I'm not going to call that Q. I'm going to call it a concentration fraction. That's what we call it, and I'm going to use the symbol C little f. I hope that makes sense, but I better put in brackets Q and put a little note. Don't know why we would call it Q other than that it is a quotient, but I want to call it a concentration fraction, and you're going to be screaming at me, but that's the same thing. And yes, it is, if you don't put in these little EQs, reminding you they have to be concentration at equilibrium. These could be concentrations anytime. And that's how you tell it's at equilibrium. Reaction is at equilibrium if the CF that you calculate equals the KC. It's not at equilibrium if the CF that you calculate does not equal the Kc. And in fact, we're going to go further. If Cf is greater than Kc, you've done your calculation, you know what the K is meant to be, and it turns out that the Cf is greater than Kc. Well, clearly it's not equal to, so it's not at equilibrium, but what else can we say? Cf will try to get smaller. It's bigger than Kc. The reaction will want to get to equilibrium, so Cf will try to get smaller. Look at the maths. To get smaller, that would imply top line smaller, bottom line bigger. Now, think of the significance of that. For the top line to get smaller, the concentrations of C and D have to go down, and A and B have to get bigger. Now, how could that happen? That would imply the back reaction would be favoured. Because if you favour the back reaction, you're going to get more A and B. That's going to make your bottom line bigger. And you're going to get less C and D. That's going to make your top line smaller. The concentration fraction will get smaller. It'll be getting closer to Kc. And eventually when it hits Kc, bang, you've hit equilibrium. And that's the use of a concentration fraction. It allows you to do concentrations, put them in that expression, the same expression. But if it doesn't equal the K, it's not an equilibrium.